All right, in this explainer, we're going to peel back the skin of the world around us to look at the mathematical blueprint of shape itself. We're getting right into one of the most fundamental tools for doing this, the shape operator. Okay, so let's just start with a really simple question. I mean, you look at these three surfaces, right? A sphere, a plane, a saddle. You just know they're different. One's round, one's flat, one does that weird curvy thing in two different ways. But how do we turn that gut feeling into a precise mathematical measurement? A measurement that works not just for the whole shape, but at every single point on any surface you can imagine.
So here's the real challenge. How do you actually capture the bend of a surface at one tiny infinitesimal spot? Think about it. A simple curve? That's kind of easy, right? You just see how fast its tangent is turning. But a surface? Whoa, it can bend in an infinite number of directions all at once. We're going to need a much more powerful tool for that.
So how do we even begin to tackle this? Well, we start by planting a little flag at every single point on our surface. This little flag is what we call the normal vector. It's an arrow that sticks straight out, perfectly perpendicular to the surface at that one exact spot. This little arrow, it kind of gives us our bearings. It tells us which way is up, straight out and away from the surface.
Now, a static arrow, just sitting there, doesn't really tell us much. The real secret, the key to this whole thing, isn't the arrow itself. It's how that arrow tilts and changes as we take a tiny step along the surface. If the surface is flat, that arrow stays pointing in the exact same direction. But if it's curved, the arrow starts to tip over.
And that brings us to the hero of our story, the shape operator. It's this awesome mathematical machine designed for one specific purpose, to measure exactly how much that normal vector is tilting, and by doing that, to perfectly describe the shape of the surface. Okay, so here's the deal. The shape operator, we'll just call it S, works like this. You feed it a direction you want to travel along the surface. That's our tangent vector v. And boom, it spits out another vector. And that new vector tells you precisely how the normal vector u is tipping over as you move. That resulting tilt is the measure of the surface's curve in that direction.
And the whole process is actually pretty straightforward, but it's incredibly powerful. You just pick a point on the surface, you choose a direction you want to go, the operator does its thing, it calculates the change, and what you get back is a new vector that describes the exact bending in that one specific direction. It's a crystal clear recipe for quantifying shape.
The source material here gives us just the perfect way to think about this. Remember from calculus, right? Velocity is the first derivative. It's how your position changes. Acceleration is the second derivative. It's how your velocity changes. Well, you can think of the normal vector, u, as the first derivative of the surface. It describes its orientation. So the shape operator, which measures the change in u, is like the second derivative. It's the surface's acceleration, its curvature. Okay, let's make this real. Let's take this idea and apply it to those shapes we started with. On a totally flat plane, you can move in any direction you want. The normal vector never tilts, so the operator's output is just 0. On a sphere, it doesn't matter which way you go, the surface curves away from you equally. And this is where it gets cool with the cylinder. If you move along its length, it's totally flat, right? 0 bending. But if you move around its belly, it's curved. The shape operator captures this dual nature perfectly. Okay, so the shape operator spits out a whole vector, which is great. It tells us all about the tipping. But what if we just want a single number? Like, how bendy is it from 1 to 10? We need a way to distill all that information down. Well, that's where something called normal curvature comes in. Basically, we take the tipping vector we got from the operator, and we just see how much of it points in the same direction we were originally going. The result is a single value, k, that tells you exactly how tight of a curve you'd be making on the surface in that direction. A big number means a sharp curve, a small number means a gentle one. Okay, and this is where the magic really happens. It turns out you don't have to check every single possible direction on a surface. Nope. At any given point on a curved surface, there are always these two special directions, and they're always at right angles to each other, that basically tell you the whole story. And these are what we call the principal directions. It's the direction where the surface bends the absolute most and the direction where it bends the absolute least. The curvatures in those directions are the principal curvatures, K1 and K2. And for anyone who's into linear algebra, get this. These curvatures, they're the eigenvalues of the shape operator. And the directions themselves, they're the eigenvectors. The math it hands us the most important information on a silver platter.
And this is just incredible. Those two numbers, the maximum bend and the minimum bend, that's it. That's all you need. It's like the entire genetic code for the shape at that one single point. And when we combine them, we get one of the most famous and powerful ideas in all of geometry.
So with just these two numbers, K1 and K2, we can now cook up a single, ridiculously powerful number that tells the whole story of the surface's shape, right there at that point. And this is the famous Gaussian curvature written as a capital K. And it's shockingly simple. It's just the product of the two principal curvatures. You just multiply them. K1 times K2. That's it. It also happens to be the determinant of the shape operator matrix. This one little number tells you, well, pretty much everything about the local shape. So what does this number actually tell us? Well, if K is positive, that means both of your principal curvatures are bending the same way. Either both are bending down or both are bending up. Think of a sphere or the top of a dome. No matter which way you step, the surface curves away from the tangent plane in the same way. Now, what if K is negative? That means your two main curvatures have opposite signs. The surface is bending up in one direction, but down in the other. This gives you that classic saddle shape. Or, my favorite example, a Pringles chip. That's negative curvature. And finally, if K is 0, that means at least one of your main curvatures has to be 0. The surface is totally flat in at least one direction. Our good old cylinder is the perfect example of this. It's curved one way, but it's perfectly flat along its length. So its Gaussian curvature? 0. Everywhere. And a plane? Well, obviously that's 0 too. So, why do we care? I mean, is this just some abstract math game? Not even close. This whole idea of measuring curvature with an operator, it's literally one of the pillars of modern physics. And the reason it's so powerful is because these tools we've been talking about, the vectors, the operators, the whole concept of curvature, they don't actually care that we're in our cozy 3D world. They can be generalized to describe the geometry of much more abstract, higher dimensional spaces. And this, right here, is the ultimate payoff. As the source material points out, these exact same ideas are what we use to describe the four-dimensional fabric of space-time in Einstein's general relativity. In his theory, what we feel as gravity isn't some mysterious force pulling us down. It is the curvature of space-time, and it's measured using this very same mathematical language we've just been exploring. So there you have it. The shape operator isn't just a formula. It's a blueprint for shape itself. It lets us translate our gut feeling about bending into a precise language, a language that not only describes the world we can see and touch, but also the unseen fabric of the entire universe. And it makes you wonder, doesn't it? What other invisible mathematical structures are out there, quietly running the whole show?